The current processes are very similar to what I would call the wildcatting of the early oil and gas days. The real challenge, though, is with with hydrogen is it's a very promiscuous gas. It really likes to diffuse. It likes to mate and react with anything it can find. I think the significant discoveries are being made in the private sector right now. Actually, I'm pretty confident of that. Mother Nature has given us, the Earth has given us an energy source. We have, at least in the United States, unbelievable resources to commercialize.
My today's guest is someone who takes thinking outside the box and extends it a few kilometers beneath the Earth's surface. A man who looks at the periodic table and sees a to-do list. Dr. Douglas Wicks isn't just a researcher, he's a pioneer tackling the mysteries of natural hydrogen, a field that promises big breakthroughs but keeps throwing curveballs at every turn. With a career spanning in innovative materials, decarbonization, and turning waste into energy, he's the kind of a mind that doesn't just connect the dots, he redraws the whole map. So, if you ever wondered whether hydrogen is the energy of the future or just a brilliant idea trapped in the Earth's mantle, Dr. Wicks is here to give us some answers and maybe challenge everything we think we know about what's under our feet. Doug, welcome.
Thank you, Ernest. That's quite a kind introduction. I would have to say I am not the one who's doing the research. I'm the one who's stating the problems and bringing together the community to address those problems.
And
I'm
you
not a problem solver. I'm a problem stater.
and quite a successful one. For the start, who is Doug Wicks?
Oh, well, I am kind of a mixture of backgrounds. I'm actually a trained organic chemist. I spent most of my career in the space of making polymers going forward. I did a stint in academics, 6 years in venture capital backed startup companies during CleanTech 1.0, looking at biomass to commodity chemicals and fuels, and then spent 6 years in the industrial mineral space, working for the French company Imerys, and have now been at RPE about 5.5 years, focusing on really critical mineral recovery, whether it's from waste or from the underground, and now moving into geologic hydrogen. The most important thing about me is the fact I'm a very proud grandfather, and will soon have my fifth grandchild, which is what motivates me to look at the future.
Yeah, that's a great answer, actually. What do you see as the core limitations in the current exploration mindset for natural hydrogen?
Um, that's a really hard question to come back and say. We've been looking at this, and RPE recently published a request for information to say, how do we begin to understand? The current processes are very similar to what I would call the wildcatting of the early oil and gas days. Individuals have assumptions, or they have a theory about where to find hydrogen, and they go out and drill for that. And There's very good people. They're finding hydrogen, so obviously they know what they're doing. But I think right now we do not have the depth of knowledge to say when we do exploration, not only to say we can find hydrogen, but to know how much is down there or how much can be produced from a given well. Um,
What gaps in our understanding of hydrogen formation processes are most critical to address for achieving commercial discoveries?
What gaps? Uh, you have to look at it and say commercial discoveries is a complex topic. Commercial discoveries means someone has to give you money to develop it. So the
Yeah,
most important limitation to developing hydrogen right now is financing. And that really comes down to the fact that if you do find hydrogen in the ground and you have a high flow of hydrogen coming out, you run to the bank and say, tell the bank, here, I have this hydrogen, give me $1 billion to develop the field. And they'll
yeah.
look at you and say, do you have 15 years production? And that's the big challenge right now. And you're going to say no. And they're going to say, we're not going to give you a check. So right now, I would say that the largest challenge to commercialization is assessment of resource sizes, is coming up with models that would say that the size of the resource that we have found. And this is very similar to the fracking revolution in tight gas in the United States. The field was, really the technology was developed in the 1980s. The first practitioners started in the 1990s. And it really didn't take off until the geophysicists and the modelers and the likes could really come back and say, this this is how we measure a potential resource. And once the potential was understood, we could map the resource. Then it really took off about 2005, and very rapid capital deployment, and which continues till this day. Um,
Talking about possibilities, USGS have calculated that Earth's underground reserves contain nearly 6,000 billion tons of hydrogen. What's your comment?
um, that's a calculation. And I look at it in a slightly different way. And this is an area we go back and forth, is that we have to try to estimate some of the basic production that's happening naturally and trapping it. And I think that's what a lot of the work from the USGS is coming back with models out of the oil and gas area. And again, those numbers that they have, we have no idea. Are they in commercial quantities? Are they within reach? Are they just small pockets, and the likes? I look at it, my focus is really looking at the chemical potential of the earth.
Mhm.
And when you look at the oxidation of iron 2 compounds to produce hydrogen, that to me is as a person who's coming out of an engineering disciplines and background, that's much more interesting because I can control that. And those numbers dwarf anything we have modeled for natural accumulations. Chemical potential.
How can geological data and modeling be better utilized to identify promising natural hydrogen reservoirs?
I think a couple of things we have to look at, and people are discussing this. We have the traditional oil and gas processes that can be used to identify gas pockets. And the question is, can we differentiate between oil and gas and hydrogen in the subsurface? And so if we have gas pockets, I think that seismic and magnetotellurics and gravitational information can really be brought together to identify gas pockets. The real challenge, though, is with hydrogen, is it's a very promiscuous gas. It really likes to diffuse. It likes to mate and react with anything it can find. So the development of large accumulations will only be present at a time when we have a rapid recharge taking place to maintain that equilibrium. And that's an area we don't understand. There's a lot of debate about the sources of the hydrogen and the migrations from the deep earth. We can look at, people talk about, the primordial hydrogen or the deep earth hydrogen coming up through the systems. We have issues around radiolysis generating hydrogen that we don't fully understand their ability to do that. And again, in the area of serpentinization or this oxidation of minerals, there's a lot to understand and how that leads to a recharge of these systems. I mean, potentially our reserves have the capability of being recharged, and this is very different than oil and gas. So that you could begin to pull on this system, and it might fill itself back up in real time. Um,
S-
and nobody's proven that yet, by the way.
and is that partially understanding from the Mali case, the recharging?
Um, there is proposal. Mali is a very unique system. I mean, it is um, you know, no one has found another one of those yet to be able to say that we have a real model. The question is why, within so close to the surface, is there, um, no microbial activity consuming the materials? And the actual source of the hydrogen isn't known.
Yeah.
My assumption is it's a very ancient system, and and though dynamic, what it's done is all the carbon sources required for microbial life have been depleted over millennia, allowing the hydrogen to charge up in there and dilute and push out the metabolic processes of ancient microbial activity. So it's a great outlier, and it's been really good to bring attention to it. But I don't think we fully understand where it's how it became that way yet.
And hydrogen being promiscuous gas or element is the best description I ever heard. So that I will jot that down.
I
Uh,
like to use that term, because
oh,
it makes people think this stuff is running around.
very much so. And in many aspects, but that one for later. So, and the next question is actually a intro for the one after it. Should we focus on reservoirs or seeps or anything else?
Um, right now, I'd have to say, given our current knowledge, we have to look at all of the above. And we don't have the time that the oil and gas industry had to develop. The oil and gas industry started by, "What? There's something coming out of the ground. Let's drill or dig here and go forward." But the really big discoveries, were not indicated by surface expression of oil. So I think we have to do both. I mean, and the hydrogen seeps are a clear indication of a hydrogen stream. Um, but again, how much volume will that unleash? We don't know.
What are your thoughts on Dr. Laren's research?
The work, I mean, you know, he's a pioneer, was a pioneer in this field, in this primordial research, primordial sources of hydrogen. Really, his interest really stimulated people to look for hydrogen, to look at the global hydrogen discovery map, and you can really tell where he had influence for that. Right now, I'd have to say, I mean, I've listened to the talks and read the papers. It is a source, and I think understanding its ability to come towards the surface, so um, the diffusion methods to the surface. If we could really understand that, we could tap into this mantle hydrogen capabilities. It's one source in my mind, and I really, as I say, I applaud the amount of work and interest he did in this. The vast majority of early researchers, on hydrogen as an energy source. And by the way, he was the first one to really propose this geologic hydrogen as an energy source. Most of the other work was done by geophysicists and geochemists and geobiologists, and they never thought about it as an energy source. It was just an academic exercise for them.
Yeah. Talking about energy source and energy carrier, it was considered all the way energy carrier. And now, in the case of natural hydrogen, it would be actually considered as the source. Am I right?
Yeah, this would be a primary energy source. And the work we do is aimed at the fact that we would get more energy out of the hydrogen we produce than we put into producing it. This is very different than electrolyzer hydrogen or steam
Yeah.
methane reforming, where
Yeah.
you're getting a huge energy penalty for making this. And so
Hmm.
it opens all types of doors towards uses that are normally we would think of as being silly. So, I mean, it's not um, out of the box to think that if we have a hydrogen source, you can just do like they do in Mali and put it right into a fuel cell and generate electricity.
Yeah.
You would never
So,
do that with electrolyzer hydrogen. That's a round trip.
yeah.
That's a circular economy with a lot of depreciation taking place.
Very expensive round trip. So, about the hypothesis, do you believe that it deserves immediate experimental verification, say testing on the field?
I'm a great advocate that we need to test all concepts in the field. We can do great laboratory work. We can do great in silico work and compute all the different things. The proof is going to be at the end of a drill bit.
Yeah.
Forward. And and again, the challenge we have now is uh, financing that is from a commercial basis is really hard, because people are going to look at it and say, how much is down there? They're going, I don't know. And uh, they'll close books and walk out of the room. And there is just the emergence of governmental activities in this area. I mean, it's the opportunities coming out of RPE were really the first competitive funding opportunities, to start understanding geologic hydrogen. And I think we need to have more of those, either from governmental basis or public-private partnerships, like has been done in the oil and gas fields. And people don't realize how much shared information and how much the different governments, paid for the basic research or the basic characterizations and resource assessments.
That makes me conclude that we are certain amount of money far from the discovery, or is it time, or what it is, and how long is the wait for a significant discovery?
Um, I think the significant discoveries are being made in the private sector right now. I mean, actually, I'm pretty confident of that. And the real question comes back to say, when's the first commercialization of those discoveries going to take place? There is a time lag that you find this, and Since it's in private industry, it's not transparent what they're doing. Um, but you need, before you come out and announce discoveries, a lot of work has to be done on flow testing and flow rates and the likes. And I believe that kind of information, that kind of work is being done now in the private sector.
You do sound like you have a crystal ball.
No, I
Or
just look at this and say, Mother Nature has given us, the Earth has given us an energy source. And when we look at it, say, and we have a rough understanding of what it is,
Mhm.
and um, and it doesn't break any laws of thermodynamics to produce it. And once we understand where we need to drill, what we need to put down, and how do we separate it out. We have, at least in the United States, unbelievable resources to commercialize this. I mean, the
Mhm.
advances drilling and reservoir management that have taken place in the hydrocarbon fields are really just amazing. Um,
So this is the first time I feel that this is not just a hype, because in your voice I hear confidence that something is just around the corner. And I believe that, you know, actually, I have a question. What technical aspects we need to make it happen? Talking about equipment, talking about, we can't really drill as we drilled for oil and gas, can't we?
and the drilling is different. We're just changing the rocks, and there's enough work. The oil and gas groups don't like to drill into hard rocks, but the mining industry has done it for a long time. There's a lot of developments now around enhanced geothermal that has increased productivity of that. I think that technically, um, if we make the assumption, there's two assumptions. One, if there's just a big gas bubble laying down there, that's real simple. You drill down, stick a straw into it, and suck it out. I don't have a lot of confidence in that taking place.
Yeah.
And I think what we're going to find is we're going to have to either drill down closer to the source rock. So we're talking about down at the basement, or we're going to have to, through engineering processes, stimulate the rock. The oxidation of iron 2 to iron 3 is a chemical reaction. It can be catalyzed, it can be moved, it can be shifted around. You can lower the temperatures, you can change the pressures. I think the big challenges that we're going to be looking at now, technically, the technical side for commercialization are going to be the gathering process. So how do we gather this if there's not a large gas field, pressurized gas field laying down there? And we have, RPE has groups looking at that, and that's publicly known, to say how do we begin to start gathering the material from the subsurface, and then how do we engineer the subsurface to increase the production? And this can be either through changes to changing the porosity of the subsurface in some way, whether electrical or mechanical ruptures of the rocks, and then can or through catalysis. Um, the other thing we don't really understand, especially in the serpentinization side, this oxidation side, is what's the ideal rock to go after for this that we can um, stimulate and shift the equilibrium to get the material to oxidize in a rapid force. That's I'm kind of going randomly here, not answering your question. Sorry.
Oh
Uh,
yeah, you
the,
are. So
the other challenge I think we I that I push continually is for people to understand that for the oxidation of iron too, this is a chemical reaction, um, and it's an equilibrium reaction. So it goes back and forth. And thankfully, this equilibrium is there, or else
yeah,
a lot of the water on Earth would be gone, oxidizing all that iron too. But it tells us that at depth and pressure, that the solubility of hydrogen in water is much higher than the equilibrium concentration. So again, that technical challenge of how do we shift that equilibrium um, to really drive what is a very fast reaction, through something called Le Chatelier's principle, where you're pulling out the reactants, and um, that's doing that in the subsurface is a great engineering challenge and opportunity.
that's a great answer to so many questions. And one of these also is which companies you think will come out first in this, and are you collaborating with the private sector, with these companies?
I will say we talk and work with the private sector. I'm unable to say who we talk and work with. It is public knowledge that there is the first unicorn on the block, Coloma, did get an RPE award.
Yeah,
So I can say, that they're in addition to the $1 million, that they received is, a small part. It allows them to look at some science outside of their commercial activities. Um, I think um, there are a number of companies that are off the radar, that are not known, that are drilling, that
true.
may be producing. I find a new one every week. Pretty much, I think there's
Yeah,
right now somewhere, it's probably getting close to 100 companies in the area, startups and large companies. Um, so who's going to be first? I can't tell. Um, you know,
yeah, yeah.
I would say, if having come out of the venture capital world, if somebody invested that much money in me, I'm sure there's somebody expecting a large um,
Yeah,
return on that in the near
that's a
future.
that's a clear answer. How do geological uncertainties impact the success of prospecting efforts for natural hydrogen?
Yeah, again, that's a lifelong endeavor for a bunch of professors to go through and look at. Um, and the geologic uncertainties that I think are most important is um, really understanding, in the subsurface, what happens when we start to produce hydrogen. The question comes back that if you look at, again, this equilibrium of hydrogen concentration in water suppressing oxidation of minerals, once we begin to pull that out, the oxidation will drive, the serpentinization will drive. Serpentinization can take place at very low temperatures and pressures. And it's accompanied by a very large increase in volume. When you look at going from an ultramafic olivinic rock to a serpentinite, you're looking at a 30% change in density, in volume. And so, what's that going to do? Um, are we going to be seeing? So that could lead to either seismic effects, or it could, which I think can be mitigated. But it also is going to be looking at production challenges as porosity gets suppressed, by these expanding reactions that take place. And the other thing we look at, that's very important to consider, is what else are we, when we start moving uh, hydrogen, out of the system and driving this reactions in the subsurface. What's going to be the impact on other materials being solubilized in the subsurface? This is a reaction process, and things dissolve. I'm actually quite surprised how much they do dissolve in the subsurface, and it's something the oil and gas people really don't think that much about. The alteration of the rocks, but we're really doing accelerated, hydrothermal chemistry down there.
And
So,
isn't it a bit strange that after so much drilling in oil and gas, we don't have a significant amount of data about hydrogen?
yeah, and again, that goes back to Professor Laren saying, he went out looking for it. Um, Part of it is they don't look for it, and the other thing to keep in mind is, again, hydrogen being that promiscuous species, and that hydrogen plus oil gives you lighter oil. So
Yeah,
hydrogen
yeah.
will react with the oil itself. It's going to react with any carbon substance, to either do through thermal chemistry or through biological chemistry. They'll have that. And the oil and gas industry really in the last, I would say 70 years, has gotten pretty smart about where to look. And so they're going to look where they expect to find hydrocarbons. In the past, they used to find hydrogen. A lot of the discoveries, being looked at it in Australia right now, are wildcatters who, back in the 1920s and 1930s, just drilling their way across Australia looking for oil and gas because there was no model. And those the wells that are now being developed by Gold Hydrogen and others in Australia. And the other thing to keep in mind is, in the early days of exploration, not a lot of people measured for hydrogen. They didn't look to detect for it. The same thing in the mining industry. The mining industry, when they drill into something, they just have an explosivity meter and they assume it's natural gas pocket they run into. So,
Yeah.
they don't look for hydrogen.
When you're
Yeah,
when you're focused on something, yeah, you don't see anything else.
yeah.
So we discussed this one a little bit, but again, what are the most significant technical hurdles currently faced by nascent hydrogen extraction technologies?
Again, I think it's going to be that gathering mechanisms and transport to the surface is the biggest technical hurdle overall. Because if you drill down into the basement and find hydrogen, it is really going to be, a lot of times is going to be highly pressurized in water. Um, and how do we separate that out and not have to bring up huge amounts of water to the surface to exsolve the hydrogen that's in there? And I mean, you can see in the videos of Barbara Sherwood Lawler, where she's drilled into fossil um, water pockets, in deep mines, how fast the hydrogen, exsolves when the pressure is released. And
Yeah.
so, how can we do that? From the groups that I look at, a lot of the work we do on the stimulation is how do we um, uh, really refresh those surface areas since it's a reaction to allow the reaction to proceed without being impeded. And there's a lot of work that I can't really discuss that is looking at methods to um, keep that reaction going as we go forward.
How can isotopic geochemistry be used to trace hydrogen pathways and refine exploration methods?
I think the isotopic and this is an area that I'll say I'm nowhere near an expert on. It is very good at giving you sources of this and differentiating between serpentinization, radiolysis, and deep earth or primordial hydrogen sources. So it gives you an idea of what type of system you're looking at. It's not an exclusive answer because I think we're going to find that these systems are a lot of them are going to be hybrid. So you're going to have hydrogen accumulation just naturally coming, hydrogen and helium concentration coming up from um, radiolysis, while at the same time you're going to have hydrogen generated by uh, serpentinization and oxidation of the ions coming forth. And so, and I think and a lot of it's going to come back to also the idea, I mean, as they're doing right now in gold hydrogen, is trying to get the age of the material, looking at the hydrogen, the helium-3 to helium-4 ratios that
Mhm.
come up. I know there's groups that are looking at different noble gases and distributions to try to understand where it's coming from. Um, it's a part of the puzzle.
Yeah. How important are the timing mechanisms of hydrogen release, and what experiments and tools could clarify this timing within the Earth's subsurface?
Oh, within the Earth's subsurface? Ooh. Um, I think that we're going to need to understand what's going down there. We're going to need really high resolution seismic and high resolution gravitometry and magnetometry to understand what's going on down there. We're going to be in a lot of the systems that we're going to be looking at harvesting um, hydrogen on the way up from the deep subsurface. We're going to be looking for really accurate information on faulting and cracking in the subsurface. Um, and understanding that, I mean, right now we can get a pretty gross measurement from seismic, but the really highly accurate information's not there, and the ability to track that information over time is not there. Well, I would say a lot of it's there. It just needs to be redeployed. I think there are people who understand earthquakes and the
Yeah.
likes, but they've never thought about applying it to hydrogen.
How can interdisciplinary research contribute to resolving uncertainties about natural hydrogen's formation and distribution?
Oh, this is an area I firmly believe we need to bring in all types of thinkers
Yeah.
to look at this. I think we're going to need to adapt a lot of the oil and gas techniques, so that brings in an entire field of understanding. We need to bring in a lot of the mining geologists understanding because they understand hard rocks and have insights into hard rocks that we don't that are not available to the oil and gas field. And when I look at this, the really the interpretation and understanding of new information is ripe for AI deployment,
Yeah.
and very ripe for the development of new sensors. I'm talking with a bunch of teams that are looking at quantum gravitometers and quantum magnetometers that really um, allow you to get real-time monitoring of changes in the subsurface, which is going to be what we need to track flows. So it's a field that, in I try to, in my public talks and in my discussions going out, I try to bring in as many disciplines into the field as possible.
You are like encyclopedia. I'm very grateful for this interview because you are really connecting the dots, at least in my head, but I believe also in other people's heads. What would you recommend as the first steps for advancing a more evidence based understanding of natural hydrogen reservoirs?
Um, I would say that, um, again, staying out of the pure private sector, and they're all guarding um, their secrets. And so when we look at general adoption, um, the work that has to be done is, again, start to bring people to really develop methods or models to come back and say, this is what it should look like. This is the impact of mineralogy and lithology. This is, um, potentials or models to say, how would we be able to detect recharge very fast, and the likes. So there's a whole set of just trying to understand that has to be done. And really, most importantly, what we need is ground truths. So we need to take these models that are out there, and drill holes. I mean, it's come back. I mean, people have some assumptions, and in the public domain, we need to, um, drill holes, validate the assumptions that they made, and see if there's hydrogen down there. And getting a dry hole is not a bad thing in the public space. If you're a
Yeah.
startup company and you have $10 million and you blow it all in one hole and there's nothing there, um, that's a catastrophe. But for in the public space, and this was done in the past for oil and gas. People, forget how much the governments in the past paid for all these dry holes that were drilled. But those
Yeah.
dry holes, in combination with, um, good holes in the public domain, allows us to be able to, really differentiate, and develop the models that allow us to increase that probability of success. Um,
Yeah. And to confirm your sort of theory that private companies are keeping their secrets, I've still couldn't get anyone to speak about it because when people are so silent, that means that something serious is happening, and of course they will open up, but just after the first real results, I assume.
yeah. You might want to talk to the group at Gold Hydrogen. They're relatively open, and Gold Hydrogen and Hytera,
Yeah,
they're
yeah.
relatively open. They aren't fully, obviously, but they're looking for the funding. The companies that are um, well funded are tending to keep themselves very quiet.
So self-explanatory. How does dehydration of serpentinized rocks as major geological process differ from other theories in the field?
Um, well, I mean, and the hydration process. I mean, first for me, it's a chemical reaction. It's a classic chemical reaction that you can look at. And as a chemist, I can look at it and say there's catalyst, there's pressure temperature effects, there's what's in your water effects. There's a whole bunch of stuff, and I will say that, um, I've seen results that say you can increase the rate of oxidation of ultramafic rocks by orders of magnitude. By classic chemical approaches.
Mhm.
Um, so, and you can't do that with, you know, primordial hydrogen. It's basically down there.
Yeah.
And it's not like we can go into the mantle and tweak something down there. We can drill to it. And the same thing with radiolysis. There is a latent amount of reactions being formed, and it really can't be accelerated. It's not subject to equilibrium limitations such as um, the oxidation processes with water. So we really can't control it. I mean, I don't think anybody's going to advocate pumping a neutron source down into the deep subsurface into an aquifer to generate reactions is going to be accepted by anywhere in the world, even though it would work. I mean, if you took, I mean, this is hydrogen generation in nuclear power plants and nuclear fuel storage is a huge issue, that they
Yeah.
deal with. So if you put more radioactive materials in there, you're going to generate more hydrogen.
So in this case, it's not an issue. Uh, what opportunities or challenges do you see in studying Earth's expansion as a potential indicator of natural hydrogen effusion?
You mean by expansion, you're meaning increases in stress and strains in the
Yeah.
subsurface? Um, Again, I think it's part of the understanding of it. We need to really, by understanding that, we'll begin to develop ideas about potential negative impacts of hydrogen production. Is it going to induce seismicity and the likes? And there are teams looking at that right now. It also, brings up the concept of saying, what does it do to faults? You know, naturally active earthquake faults, and so in countries like Japan, um,
Yeah.
doing something in a fault is not really looked on very favorably until we develop that information. I think, again, I think it's part of a puzzle. We're early enough in the development of this field that we need an all of the above approach.
How does the idea of hydrogen influencing Earth's geodynamics challenge current geological models?
I don't know if I can answer that. That's a good problem. Um, again, I think and by yeah, and again, I think it's going to come down to, as I say, that expansion issues,
Mm.
and what that does to the subsurface as you squeeze and push on things. We're going to need to understand that.
I would love to hear your predictions.
My predictions. Well, the sun's going to come up tomorrow. That's a sure bet I'll give you. Um, my predictions are that um, you know there will be natural or geologic hydrogen, entering the economy by the end of the decade, in a noticeable amount, and um, especially if we, can, and the depth of that impact is really going to come from, the total impact on the energy space is going to really come down to, can we make it a financeable program by understanding, resource potential for a given field. That's going to take place. I can also say that, as we develop the systems, I am a firm believer that we are going to that published information out there about costs, having it around $1 a kilogram, is not unrealistic. And at a dollar a kilogram, in Europe, that would make it competitive with natural gas pricing right now on a
Yeah.
thermal basis. And it would be very competitive in Japan
Oh,
on a natural gas basis. That um, I mean, a very simple thing to think about is you multiply the price of your kilogram of hydrogen by 8.6, and that gives you the thermal equivalent price in natural gas. So at a dollar a
yeah.
kilogram, natural gas would have to be 8.6 or $8.06 per million BTUs, which is double what it is in the United States right now.
Yeah.
But that's very much equivalent to what's being paid in Europe. And I don't know the translation of the kilowatt hours.
Doug, thank you so much for being my guest today.
Good.
It was truly an honor and very informative, interesting, and predictions are great.
Yes. As I say, the sun will rise tomorrow. That I am sure of. So
Thank you.
thank you.